Dear guests, if you need simultaneous translation, please pick up earphones because there will be comments, questions in Armenian if you're English speaker. Բարի երեկո բոլորին, եթե դուք թարգմանչան պետք կարիք եք ունենալու, ականջակալեր կան, կարող եք վերցնել, որտեվ խոսնակը անգլերենով է ներկայացնելու, բայց հետո հարցերը կարող են նաև անգլերենով լինեն։ Մենք երկու երեք պես կսկսենք, որտեվ Հայաստանում ենք։ Good evening, dear friends, colleagues. We are very excited to have this evening's talk. I am very excited because it brings two worlds that you often don't connect with each other. Of course, it's very natural when you think about it, but you know. So in the beginning was just fire and hell, right? It was a lot of gases and so on, and then it kind of congealed, and then it became kind of eventually hydrosphere, geosphere, and then miraculously life appears, right, under these circumstances. And it's not very far into the development, right? 300-400 million years, and we start to see single-celled life. And then, of course, it takes another few billion years to have multi-celled organisms and very complex organisms, and invasion of plants and of land and so on. And so the question is, how much did the geosphere that we had by then and the abiotic environment we had back then impact the way life evolved? And for me, the more kind of crazier idea that Dork wants to pursue is that actually biology also impacts geology. So maybe it's crazy for me and it's common sense to geologists, but you know, so let's see. So, but before that, let me introduce our president, Dr. Bruce Bohosian, who will give introductory remarks. Also, we thank, of course, the Fulbright program for supporting Dork's visit to Armenia, who is being co-hosted by us at the College of Science and Engineering at the Akopian Center for the Environment at AUA, and also National Academy of Sciences, Institute for Geological Sciences. So, and Khachatur Meliksetyan, the director, is here, and we only hope that, and part of Dork's visit was to increase the collaboration between AUA and the Institute. So with this, Bruce, please.
Thank you, Alan, and good evening, everybody. Next October, Armenia will host the 17th Conference of Parties, or COP17, of the Convention on Biological Diversity. And during that time, about 30 or 40,000 participants from all over the world will come to Armenia for most of 2 weeks to discuss issues of biological diversity and the world's collective responsibility thereto. The hosting of this, a conference this large in a country this small really necessitates building awareness among the general population about the importance of the conference. So the United Nations has initiated the Road to COP17 initiative to underscore the importance of COP17 in really every corner of Armenian public discourse through all segments of Armenian society. This year-long series of activities is a joint effort of the Secretariat of the United Nations Convention on Biological Diversity and the Ministry of Environment of the Republic of Armenia. And they've chosen only one academic entity in Armenia to participate in this planning alongside them. And we're very proud to say that this is AUA's Agopian Center for the Environment, which Alan directs. Today, we're delighted and honored to welcome Professor Dork Sahagian to deliver today's talk as part of our contribution to the Road to COP17 initiative. Professor Sahagian is a professor of Earth and Environmental Sciences and director of the Environmental Initiative at Lehigh University in Pennsylvania. He contributed to the Intergovernmental Panel on Climate Change Reports, which received the 2007 Nobel Peace Prize. And he served as principal scientific reviewer for the United Nations Global Environmental Outlook, Also, for the fall semester 2025, we're delighted that he is a Fulbright scholar, both here at AUA and at the Institute of Geological Sciences at the National Academy of Sciences of the Republic of Armenia. Professor Sahagian holds degrees in physics, geosciences, and geophysics from Rensselaer Polytechnic Institute, Rutgers University, and the University of Chicago. His research spans paleoclimatology, volcanology, geodynamics, hydrology, and the environmental impacts of human activities. Among many other things, he's well known as the inventor of a technique for calculating the Earth's air pressure in the past based on the difference of size of bubbles in solidified lava, volcanic lava. He is the author of A User's Guide for Planet Earth, and he played a key role in establishing the Biogeosciences section of the American Geophysical Union. His work focuses on integrating diverse scientific disciplines to better understand the Earth's systems and global environmental change. Just to add to what Alan said just a bit, many of us have a mental picture of the planet Earth that partitions it into a living part, what we might call the biome or the biosphere, and a non-living part consisting of, for example, minerals, oceans, and atmosphere, what we might call the geome or the geosphere. And thanks to scientists like Professor Sahagian, we often hear about the impacts of the biome on the geome. This could include natural effects, for example, the formation of oxygen in our atmosphere due to the presence of life on Earth, or the sequestration of carbon in the calcium carbonate of seashells. But they might also include anthropogenic effects, such as the release of CO2 from burning petroleum products, the effects of agriculture on soil, or the effects of mining on the Earth's lithosphere. In today's lecture, Professor Sahagian will describe why this impact works both ways. The geome also impacts the biome. We, after all, ingest minerals from the Earth whenever we eat food that's grown in soil. And we know, by the way, that the volcanic soil of Armenia is responsible for some of the finest wines in this region. So there's a real life example of the benefits of good geology affecting biology. The point is that the geome and the biome have functioned together as a sustainable system for billions of years now, and only by understanding this codependence can we appreciate how we arrived at it, how delicate it is, where it's heading in the future, and how easily it might be thrown out of balance. So I think this promises to be a very interesting talk. I've been looking forward to it. Please join me in welcoming to the podium Professor Dork Sahagian.
These lights turn off? Must be a way to get these lights. My pleasure to be here, and
Dork, I think you need to speak into the microphone so there's a translation. Dork, you need to speak into the microphone.
I know, I just wanted to bring it back to the beginning. Okay, does this work?
I don't know, does the translator hear? No.
Does everyone hear me, including especially the people in the back room?
The important thing is the translator.
Yes, the translator is the most important one, absolutely. Very good. So, well, thank you. I'm going to attempt in the next hour to describe life, the universe, and everything. The answer, as we all know, is 42. Well, with my apologies to Douglas Adams. No, it's not really 42. In fact, it all comes down to time and space. See if this one works better. You hear this? No? Yeah, that's working better. Okay, good. Okay, so time and space. So time is long, right? Starting about almost 14 billion years ago, stuff got made. Our galaxy is pretty old in those terms. The Earth and the sun of the whole solar system is much younger, right? Only about not even 5 billion years. Moon, yours, and Mars younger than that. And we think of the history of the Earth in terms of this big clock. And so if we start at midnight, come around through the early hours of the morning, eventually we get some life early on, very primitive, later more complicated life, more and more complicated life, and eventually people a few seconds before midnight, right? So that's, you know, so I'm afraid my clickers, okay, so you saw the time scale. The time scale is based on extinctions of life. So geology defines itself on the basis of when organisms lived and died. Which brings in time an important evolutionary concept. There's uniformitarianists, these are big words, and uniformitarianism ascribes to the idea that all of evolution of rocks, geology, life, people, everything goes on slowly and gradually, and eventually we get to where we are now. Catastrophism, on the other hand, ascribes to the notion that everything stays the same until something big and bad happens. And that's when it changes everything. And it turns out they're both correct. So let's look at stuff. Stuff. You know, I'm going to turn this around. This clicker's not working as well as it should. This will be better. Okay. How about the stuff? We're made of stuff that came from when stars started. And how are stars made? Well, I wrote a little silly poem, limerick, to describe that, right? The nebula looms as large as can be. Not spins to disk, mostly H and HE. The star lights the day, the gas blows away, and what cleans it out is you oversee, you being light intensity, c being the speed of light, and you have to be an astrophysics nerd to appreciate this kind of thing, right? And the sun is a very boring place, right? It's right here in the main sequence of stars, kind of in the middle, very average, very normal. It's been around almost 5 billion years. It'll be around another 5 billion years. So we're about halfway through the life of the sun. At the end of 5 billion more years, it's going to grow up into a red giant, engulf the Earth, burn it all up to a crisp, and that'll be the end of life as we know it on Earth. So we got about 5 billion years to figure out what we're going to do. So what happens in a star? Well, in a big star, you get little nuclei turning into bigger nuclei through fusion, and eventually things can turn into iron, which is the most stable nuclide there is, right? From iron, you go nowhere. To make anything bigger than that, it takes something special, which is the pandemonium of a supernova, which is where we get our big elements from. So what we have in the solar system and on the Earth is we get, you know, sure, plenty of hydrogen and helium, but all these bigger things that come from previous supernovas. So we're kind of using the leftovers from previous stars and previous solar systems and other galaxies. So we are basically star stuff. So bring in the Earth, all the bits and pieces necessary, all the elements, all the building blocks for life are there. But the environment was very unsuitable, too hot, right? So we had lava covering the planet. We have, you know, boiling rocks. then contraction, gravitationally, all kinds of nuclear reactions going on within the planet that heated it up to the point that nothing's going to be useful until later when we could have a crust that was cool enough to stay on the surface. Somebody could walk around on it. But that doesn't come till much later. A place you didn't want to be, especially when the moon formed. This is a bad place to want to be alive. And there wasn't. But throughout volcanic processes that brought all this material to the surface, it also brought water that made the oceans. And the oceans are where life began. Another factor that happened and continues now is tectonics, which is the motion of the plates driven by mantle convection. And what happens is that the plates keep making mountains and keep making land. If not for that, erosion of all the mountains and all the lands would cause everything to go into the oceans, and we'd have a water world with no land to walk around on. So convenient for tectonics that it's alive on this planet. Then about 3.7 billion years ago, we had a special development. Beautiful. Now we have life. Well, there's been a few major events in the history of life, right? Got to be self-replicating. We got to use the sun. We made fancy cells. We got fancier and bigger, and eventually we claim intelligent. What's next is not clear. So looking at the big picture, here we are in the beginning of the first life, and we've very much diversified. Right? Life is much more diverse than it was. And I tell my students, always think critically about what you see. Don't believe anything you read. Don't believe anything you hear. Don't believe anything anybody says. Don't believe anything I tell you. Right? Figure it out for yourself. So what's wrong with this picture? Well, I'll jump right to the punchline. There's a decimal point missing. All right? The Earth is not 45 billion years old. All right? So somehow that got through editors. So the first signs of life were RNA, ribonucleic acid, which is a precursor to DNA. So we had a world of RNA for a short time that could do all the things that life needed: replicate, metabolize, move, do other things that needed to do in a RNA world for a time. Then DNA shortly followed. A little after that, we figured out how to use the sun to make biomass, right? And we do this, but a very simple reaction in the end, never mind the biochemistry involved in photosynthesis. But we take carbon dioxide and water, turn it into sugars, and it gives off oxygen, O2, right? And as you probably know, when animals do the other way around, eat sugar, breathe oxygen, they exhale carbon dioxide and water, and that's respiration. So oxygen started developing, right, into the atmosphere. Well, it started out going to the ocean, right, and it took a long time to become significant in the atmosphere that actually you could have plants on land. And the rise of oxygen on the planet, O2, was very odd and syncopated. Because the first thing that happened when photosynthesis, these photosynthesizing microorganisms, were making oxygen in the ocean, turns out O2 was poison to these cyanobacteria. So they exhaled this oxygen into the ocean. It was not good for them. Well, the iron that was into the ocean rusted, basically iron, right, made magnetite, that sank to the bottom of the ocean. And the rest of the oxygen basically killed the cyanobacteria. So they died out. Well, that's too bad. Then the oxygen that was remaining precipitated silica, and it made a very nice chalcedony. So that depleted the oxygen again, and then Narayanini, the cyanobacteria, could bloom again. And they did that again, made more oxygen. This cycle went back and forth for about 1 billion years, and made these pretty rocks, right, called banded iron formations. So here's life and death, making rocks that are particularly beautiful all over the world. And that's fine oxygen was poison in the oceans, right? Poison to the cyanobacteria. There wasn't much in the atmosphere yet. And that's a problem in the atmosphere because ultraviolet radiation, UVC, the high energy radiation, is deadly. Nobody wants to be anywhere near UVC. And O2 in the atmosphere absorbs UVC, right? Water also absorbs UVC, so the cyanobacteria were kind of okay in the ocean, right? But life had no chance on land until later figured out, okay, it took 1 billion years for the cyanobacteria to figure out, let's make some protection from the oxygen poison that we're expelling. And they did. We made eukaryotes. So that's great. Now suddenly life is booming. We can really move and make multicellular organisms, right? Now we're getting fancy. So this is time to really start changing the environment. And then, joy of joys, we figured out that we don't have to make the same organism that we just were. We can get together with some other organism, combine our genetic material, and have a much more diverse set of offspring who can adapt to changing environmental conditions. All right, this is where biodiversity really got going and where life really started altering geology in such a way that almost half of all the minerals on the planet are made directly or indirectly from life. Mars and the moon don't have as many minerals as we do. They don't have life. So it's an amazing thing. So this boring billion years went by when all this was going on, but to be fair, it goes the other way around. There are certain minerals that were needed to make these complex molecules that started making life in the first place. So it's a two-way interaction between life and the biosphere. Okay, fast forward a billion years or so, and we got another major event in life, and that's skeletons. Now this is kind of recent times, right? Only in the last 500 million years, right? But we didn't have people walking around. The first skeletons looked more like this, somebody swimming around like fish. Well, that's fine. Time went by, and finally, enough oxygen developed in the atmosphere to absorb the UVC, right? So now the surface was safe for life on the surface of the planet, and people, meaning plants, could come out onto the ground and live. They were followed immediately by insects, and shortly thereafter, the fish in the ocean said, hey, here's some dry land to go on. Let's go eat some of those plants and insects. But they still had to go back into the water to reproduce until along came the amniotic egg. Hey, now we can reproduce on land. We don't have to rush back to the ocean, so we can go all over the land surface, right? And reptiles took advantage of that. So everything was going great until we started getting extinction. Extinction was a big problem in that an entire species gets wiped out, not in one place, but in the whole entire world. When you have lots of species wiped out, so many that all of them in a genus gets wiped out, all the genera in a family get wiped out, then you start getting a mass extinction. And we've had several of those, 5 big ones in the last 500 million years, right? And those are these guys. So the trilobites all lost it at the end of the Ordovician. End of the Permian was the biggest extinction of all. 95% about of all species were wiped out, right? Everything that's here today is left from that 5% that remained, right? But it happened again and again. By the end of the Cretaceous, right? Okay, only 76% of the species are wiped out, but that was a big one. And we all know what happened at the end of the Cretaceous, right? Wiped out the dinosaurs and ammonites and many other major groups of organisms. But something else has been going on, and that brings us back to one of my favorite subjects, volcanology, right? Where at various times throughout Earth history, there's huge outpourings of lava, basalt, that made flood basalts, the Siberian traps, the Deccan traps, and many, many others over time. And wouldn't you know, each of these is correlated, each of these major flood basalts is correlated with an extinction, a major mass extinction at a boundary that's defined by geology. And the geologic timescale was made long before we could date when these major outpourings of lava were. And it's not just the lava that changed the environment, it was the gases and especially aerosols and sulfate aerosols that changed the climate and conditions in a way that was very bad for anybody that was alive at the time in the oceans and on land. So here's all these mass extinctions, right? Major mass extinctions at various times. This is the big one at the Permian, right? Well, that's something. But still, despite those mass extinctions, biodiversity has increased over time, right? It's been hit a few times, but it bounced back. What that means, though, is that the ecological niches, and a niche is what an organism does for a living, what it eats, where it lives, how it reproduces, what it needs to do. And you can't have two different species in the same niche. One will outcompete the other one, right? So the niches have been getting narrower. Everybody's been getting more specialized, right? And that's not real good for the species because if something changes, you can't cope with it because you're too specialized, right? At the same time, the whole ecosystem becomes more robust. And why? Because with species in such close, narrow niches, one niche can move into the next one and take over, right? And this is happening right now in some places where we've gotten rid of wolves and the coyotes are getting bigger to take the big game that the wolves used to be taking. So this is happening in real time. We can watch it. So that's okay. So what do we have now, right? Well, millions of species, we think, right? Okay, some have been described, some, but most we have no idea, right? We don't know. But we do know is that many are becoming extinct. We can see them. We saw when they were. We saw that now they don't exist anymore. And why? Well, we're taking away their habitat. We're taking away what they need to live. So one thing we've learned is that kind of the bigger they are, the sooner they fall. These large mammals became extinct first, then the smaller ones. And of course, we all know that the cockroaches will outlive us all. It's pretty much going to be the way it goes. So what do you have to do to avoid extinction? Here's my advice. To avoid extinction, right? Be small. Don't need to eat a lot, right? Reproduce fast. Have lots of babies all over the place. Be able to live anywhere, right? Eat anything you want. It'll all be good, right? Be able to adapt to evolving conditions. Be a generalist. And maybe most of all, just be lucky, right? So a lot are not so lucky, right? So here's mammals, our feathered and furry friends that we all know and love. We know how many are threatened. We know how many are already extinct. But amphibians are the most vulnerable. They need to go back to water to reproduce. Water gets polluted. The wetlands get changed. They're our canary in the coal mine. But there are a lot of other species, most of which we don't even have records of, right? And there many are threatened. Others may become threatened. But we know, if this is pretty low down on the screen, we know how many are already gone. We don't know how many still remain, but we know how many have already become extinct. Well, how about people? People almost became extinct about 73,000 years ago when there was yet another huge volcanic eruption, Toba. Toba was so big that it wiped out most of the people in the world, and it led to a genetic bottleneck. So what happened is, in Indonesia here, it wiped out a large area of the world in terms of people, but a few pockets remained here and there, right? And about 40 to 10,000 maybe reproducing females made it through. Sorry, boys, only the girls matter for this kind of thing, right? Boys don't count, right? So okay, that's fine. But what that happened, so we had a large population of people. It got very small, right? And then got big again. And you could talk to anthropologists about which genetic lines became extinct, which continued in various parts of the world to lead to what we have today. And what happened there is that because of this major eruption, those few survivals all over the world were genetically very diverse. So because of that, human biodiversity that we have today is much more than it would have been if all those survivors were the same genetic family, as it were, right? So we had very different genetic codes from different parts of the world. So we would not have this much diversity if they weren't in different places. Now, the anthropologists are still arguing about some of this because apparently the way they follow the genetic lines through the mitochondria for females and the Y chromosome for males, and the time is mismatched a little bit, so they got to work on that a bit more. So we finally come to intelligence and culture. What has that done for us? Well, some stuff, right? But it's not all that bad, right? There's a silver lining there for intelligence and culture. But one thing that's happened in the here and now where we are is we're changing climate. That's a big one. Now, don't confuse climate with weather. Climate is a long-term environment, and the weather is just what happens on a day-to-day basis. That's simple. But looking at the long view, when the Earth began, 4.5 billion years ago, the sun was not as bright as it is now, right? So we had a faint young sun. And it got brighter and brighter. In the meantime, life, through photosynthesis, took the CO2 as a major greenhouse gas and other greenhouse gases and took it out of the atmosphere to counteract the brightening of the sun so that the temperature of the Earth has stayed between the boiling point and freezing point of water for 4.5 billion years. That's pretty amazing, right? Which brings us to the Gaia hypothesis, which, okay, life affects its physical environment. Yes, it does, right? Life has altered its planetary environment such that it persists. Yes, it has. Life controls the environment on purpose? Maybe not. I don't think the cyanobacteria got together and had a big conference to decide that we're going to make eukaryotes to protect ourselves from that poisonous O2, right? So this is where it gets a little bit like Avatar and stuff. This is not science. All right. But on the medium time frame, right, we have changes in climate caused by changes in the orbital parameters of the Earth, right? And these led to ice ages and interglacial times over the past. And by the way, this was made by a geologist in which time goes right to left. Physicists have time going left to right. So, and you can see the carbon dioxide going up and down between 280 and 180 parts per million, and the temperature following suit, right, until the Holocene, last 10,000 years or so, has been very stable climate. So in the shorter view, what do people do, right? Well, a few things. We emit gases, we use land, and we move stuff around, right? And we change the planet thereby by all these things. We change the land cover, we change the climate, we're leading to a mass extinction. So here's some very simple observations. You can look at the history of human population, right, for the past several thousand years. Whoa, it climbed up so quickly, right? If any other species had a population curve that looked like that, we'd call it an infection or a plague, and we would do something about it, right? No surprise, the carbon dioxide in the atmosphere looks the same way. As a result, climate has been changing. We've been warming up. We'll talk about that in a minute. We've been fixing, through the Haber-Bosch process, more nitrogen out of the atmosphere to make fertilizer than all the bacteria and all the soils in all the world, and we surpassed that in the 1980s. As a result of agriculture, right, we've been changing the surface of the planet in such a way, right, for agriculture, that we've driven a number of species on a one-way ride into the fossil record. So what do people do? Okay, we know where emissions come from. We know what land use is. We even know, we think we know what the new owner of this cornfield is going to do. They're going to plant another crop of corn? Nah, they'll probably build condominiums, right, or something else. They certainly will not let the land revert to its original ecosystem so that it will become a habitat for species. So we've been measuring carbon dioxide in the middle of the biggest ocean, right, at Mauna Loa Observatory in Hawaii, and it's been increasing. Okay, we know that. As a result, the temperature's been increasing most rapidly, most recently. And you put the two together, and you see the carbon dioxide concentration going up, right, with the temperature. So going back 500,000 years, right, we have interglacial, cycloglacial, interglacial, glacial, right, between 280, 180 parts per million of CO2 in the atmosphere until the Industrial Revolution, and now we've shot up to 425 already, on our way up to something much higher, right? So we've broken out of this envelope, this natural envelope of carbon dioxide concentration in the atmosphere. That's a cool experiment, right? I mean, scientists live for this kind of thing. Let's take a planet, let's change the atmospheric composition to alter the radiative balance with the star and see what happens. It's kind of cool, it's fun stuff, but I mean, it'd be convenient if we didn't have to live on the planet that was doing this experiment, but that's what scientists do. So where's it coming from? Well, until recently, the U.S. was the biggest emitter of CO2, but China has far surpassed that. So you can make a carbon budget, and we've done this for decades. And some time ago, we figured out where the CO2 is coming from, where it's going to, but we couldn't account for some of it. Some of the emitted carbon was going somewhere we didn't know where it was. There was a missing sink. A missing sink? Where did it go? Well, it's okay. Subsequently, it was found in the terrestrial ecosystem because we were not sufficiently accounting for the amount of dissolved organic carbon going through rivers into the ocean. So finally, we could close the carbon budget. So we know where it's coming from, right? Emissions and land use, and it's going into the atmosphere. Some of it's going into regrowth of Northern Hemisphere forests, and some of it's going into the ocean to dissolve and lead to greater carbon dioxide in the ocean, which is leading to ocean acidification, another problem. So where are we going with all this? Well, my crystal ball is about as fuzzy as anybody else's, but it depends on what we decide we're going to do, right? So, some people have identified a problem that, okay, we're exploiting natural resources, we're externalizing our environmental costs, and we're leading to disruption of ecosystems, extinction, loss of biodiversity that we'll talk about a lot next year. And why? Well, we know why, right? It's the things people do, right? It's a very simple problem. So what do we do about the loss of biodiversity? Well, we could just preserve it in seed banks and genetic banks, hoping that someday we'll come to our senses and have an environment on the planet that they can live in the wild. Maybe, right? We're doing that. So what is sustainability anyway? Well, it's well known from the United Nations Brundtland Commission in 1987, meeting the needs of the present without compromising the ability of future generations to meet their own needs. Sure, but we cheat because our needs are vast. We need to have lots of children. We need to eat lots of meat. We need to burn fossil fuels. We need to be consumers, right? But future generations' needs will be much more meager. So perhaps we should have a little bit of a different definition, right? What is sustainability? Doing what can be done forever by everyone, not just wealthy Americans, right? Without adversely impacting environmental conditions or depleting the resources that enable everyone to continue doing it forever, right? So where does science come into that? Well, who needs it anyway? Well, back in the day, right, just bring home the food, develop some weapons, some nice obsidian, some nice Armenian obsidians, which are fabulous. If you've ever been out to look at them, they're wonderful. So science, started out. But since that time, there's been some developments in science, right? Aristotle had some logic. Da Vinci had a code. Archimedes made a screw. Galileo got screwed. Madame Curie needed a cure. Newton made some laws. Einstein refined those into theories that Hawking refined further, right? So who's going to be the next one in this frame to change the way we think of the view of the world and where we're going? Maybe it'll be an AUA student, right? Yay, okay, maybe. So in the 20th century, the scientific community was viewed as industrialists. We were so good at this. We developed industry, we exploited natural resources, we developed the economies to the point that in the 21st century, we have a different set of problems to solve, right? And so, what have we done? What have we discovered over time? Fire, right, which my mother claims was first tamed in Armenia, right? And where did that lead, right? Okay. The plow, right, with agriculture, that was huge, right? Led to some other issues. Electricity, what could be wrong with that? Well, okay, we'll use it. How about medicine, right? Where did medicine go? Well, to huge populations, right? So I call this the millennial transition because in the 20th century, we were industrialists. In the 21st century, we're treated more like physicians. This is what the Agopyan Center is kind of about, right? Going to fix the issues once we can identify them. Which brings us to economics. The ecosystem, the global ecosystem, including the geosphere and the biosphere, provides us goods and services we need at a fixed rate, right? So you can think of this as the capital of the ecosystem providing interest for us to live off, right? And as any trust fund manager would tell you about some trust fund kid, right? I think this is Paris Hilton. Any trust fund manager it would be anathema for the spoiled little brat to eat into the principal. You only have to live off the interest, right? But in the 20th century, as a result of scientific developments and technology, we figured out a way to eat into the principal. As a result, in the 21st century, we have to figure out how to get more yield from less principal. So that's the challenge for all of us. Brings us to Greek mythology. We all know Greek mythology, right? Way back in the day. Well, risk is defined by the probability of something bad happening times how bad it will be if it does, right? That's the risk. You know the story of Damocles. There was a king back in mythological times, and he was sitting on his throne, a big sword over his head, hanging by chains, and it was unlikely that the chains would break. But if they did, it would be all over for Damocles, right? So it was low probability, bad impact, right? And I'd put Medusa over there too. I don't know why Medusa's over here, because I don't want to turn to stone, right? So, okay, with Pandora, you don't know what you're going to get. You open that box, who knows, right? Where you don't want to be is out here with Cassandra, where Cassandra is given a gift by the gods to be able to foresee the future, and a curse from the gods that when she spoke, no one would believe her, right? You don't want to be there, because you know it's going to be bad, and it's going to be real bad, right? And some of the scientific community feels like that these days, right? So we know some of the risks and consequences of human activities. Anybody see this a few weeks ago? Yeah, it was right here, right? So a few years ago, this happened in New Jersey, right? There was a hurricane. Hurricanes are going farther and worse, stronger anyway, than they used to be. My cousin's house was right here. She didn't ask me if she should put a house there. Right? I just said no. By the same token, people ask, why do I study volcanoes from Pennsylvania? Because I know better, right? Okay, so this is what happened in New York from that same hurricane, right? So this is never happened before. The ice is melting in the Arctic very quickly. And so we're going to have an ice-free Arctic pretty soon. So we have to change our maps, right? This old Mercator projector, that Mercator projection is not going to be useful anymore. Now we need a polar projection of the Earth. People are going to be moving farther north. So trade routes will change, right? Because we can go through the Arctic now. It's much shorter to get there, right? Who needs those canals with the pesky pirates, right? Which has some geopolitical implications, because those nations that border the Arctic now will have a stronger position, right? And Norway blocks Sweden and Finland from the Arctic with a little bit that touches Russia. Right? We'll see what happens. Well, we like to think the Scandinavians are so civilized, they'll work it out, right? Yeah. Agricultural yields will change. Wet places are expected to get wetter. Dry places are expected to get drier. It's the dry places that are the most vulnerable. As it is already, in most of Armenia, we have to irrigate our crops, right? Not from natural rainfall, for most of our agriculture, right? This becomes vulnerable, right? So you can see how the changes are expected in many parts of the world. You know, the red is a reduction in crop yield where so many people live. Fertilizer is very useful for growing crops, helps them grow, especially when we deplete the soil. Phosphorus is one of the things we need in fertilizer, and we're running out. We don't know where phosphorate came from. We don't even know how it was made. An odd thing. Geologists need to work on this because we don't know how to make more phosphorate when we use this stuff up. Well, one of the things that is expected to happen, and has already happened, is sea level is rising. So if the ice melts, the US will look like this. Goodbye, Florida, and many other places, including New York, Los Angeles, Philadelphia. So you can look at present world. 5 meters of Greenland melts. 50 meters of Greenland and Antarctica melts. Twice that, not going to happen soon. 3 times that, now we're going back to Cretaceous times. So that will take millions of years to happen. So what's the natural result? It's not me. Well, okay, we could go there if people want to, but I don't think so. So what do? There's 2 options. You can mitigate or you can adapt. Mitigation is basically stop bad things from happening, right? Okay. Adaptation is deal with them better when they do. Be ready for them, right? So in walks in the Intergovernmental Panel on Climate Change, IPCC, which back in 1996, you know, the best that the politicians could do, because they write the reports, right? The scientists only inform. The balance of evidence, there may be a discernible signal from people. Well, 2001, most is attributable to human activity. Attributable, okay, good. 2007 now, this is when the Nobel Prize came into the picture for these guys, right? Most is very likely to be caused by people. Time went by, 2013, the next report, it is extremely likely that it was caused by human activities. 2021, okay, it's unequivocal, it's sure, we know, it's people, right? So the scientific community has known this the whole time. Finally took all these decades for the political community to get around to acknowledging it. The basic result is things are going to warm up, right? And the consequences of those are going to continue for decades, about 0.2 centigrade per decade. But even if we hold CO2 in the atmosphere constant, it will continue to warm up, right? So eventually we have to have emissions go to 0 and find ways to remove CO2 out of the atmosphere to get down to somewhere closer to pre-industrial conditions, or at least to 1.5 degrees warmer than pre-industrial. So, well, what does it cost? People always worry about the money, right? Well, the cost of mitigation is changing our energy network, right? The whole portfolio needs to change. Well, there's a lot of money invested in that, right? That's fine. In the US, got to reorganize community structure so you don't have to drive one place to another, okay? You know, not like Yerevan, you can walk downtown if you want to, right? The cost of adaptation, though, just imagine the cost of buying a condominium in Miami. I mean, I can't afford one, but maybe, you know, some people can. And then buy the next one, all up and down the floor. Now buy the entire building. Now buy the next one, and buy all of them, and then all the schools, all the roads, all the infrastructure, everything. What is the value of that? It's huge because it's going down, as you saw on the map, right? So what is the cost of that alone? Never mind then the agricultural losses, the disease vectors, and the rest. So when you calculate all that, the cost of adaptation is huge compared to mitigation, so it's worth mitigating to any economist, right? So how do you do that? Well, the main thing is convert to sustainable energy sources. Well, now I have a friend, Jonas, who said, I don't have any kids, so I'm not the problem. I want to keep driving my truck, burning fossil fuels, not recycling. How many of me can we sustain forever? Good question. So I did a little calculation, figured out basically all these, the coal, gas, and oil we've got, and it came out making some rash assumptions about continuing to generate these fossil fuels at the same rate that we have for the last couple of 100 million years. And it came out, you know, about 50,000 Americans like Jonas could be supported forever. Sadly, we already have more than 50,000 Americans, and we got 8 billion more that want to consume like Americans. So that's not going to work. Energy all comes from the sun, as we know. Oil, gas, and coal came from the sun millions of years ago, concentrated in nice, convenient chemical form. So the rest is in real time. These don't come from the sun. Nuclear, meaning, well, it came from a previous exploding supernova, so we get uranium. Tides come from the moon and stuff. Geothermal comes from within the earth, right? So when you have this convenient chemical concentrated solar energy in the form of fossil fuels, how can we compete, right, with the sustainable energy sources? The problem is, what's the actual cost of fossil fuels, right? We pay only for the cost it takes to get them and bring them to you, deliver them to you, right? What does it cost to make the stuff? Well, we don't care. We didn't make it, right? Reminds me of cell phone, you know? I bought a cell phone, bought it from a company that invented it, designed it, produced it, marketed it. I give them money, and they use the money to make more cell phones. But I could have bought it from a kid who stole it off a truck, right? Might not have to pay as much. And why? Because the kid has no intention of using the money to make another cell phone. Now, I can buy energy from a sustainable energy company, and I'll give them the money, and they'll use that money to keep making more energy and keep producing the energy in a useful form from the sun, right? Either from solar, wind, geothermal, right? Or hydro. Fine, right? Or I could buy some fossil fuels from a fossil fuel company, and I'll give them money, but they have no intention of making more coal, oil, or natural gas out of that, right? So no wonder. So what do we do? Tough one. One thing, it's not going to be possible to do anything until we can alter the mindset of people. What do we call ourselves? I'll give you a hint. We call ourselves consumers. We have consumer rights, we are consumers, we consume. We don't consider ourselves preservers or sustainers, much less restorers. So I'm driving my little Honda Civic. This is in Maine, in the United States. I said, oh, I don't know if I can park here. There's a sign, it's probably special. Turns out the sign says, fuel efficient vehicle parking only. What are these guys? Huge behemoths. I managed to squeeze in there, but fuel efficient compared to what? Right? Well, even this guy. This is the conservation officer driving a big SUV. Really? Okay, here we are at Lehigh University. Can you find my car amongst all these huge vehicles that it takes to get one person to come to the college? Oh, there it is. Yeah, okay, so you get the idea here. So there's a disconnect between science and policy, meaning, what we do about it, right? So what we know, we know. What do we do about it, right? And scientists cannot solve problems. All they can do is provide information and knowledge, right? People have to solve the problems. And it's surprising sometimes. Well, why don't they listen to us, right? It's like, gee, well, who would you trust, right? Who would you trust when somebody says something? The distinguished gentleman or the wild-eyed scientist that speaks in some foreign language you don't understand with fancy equations, right? Why can't we communicate properly, right? Well, in part, there's language barriers. The scientific community uses words very differently, like a theory. Well, it's not, in the public, they think it's something very different than the highest level of scientific understanding, right? Bias, oh, that's terrible, you can't have bias. No, it's just observation. How about scheme? A scheme is not a devious plot, it's a systematic approach to solving a problem. So we use different words, right? And it's not just the words we use, it's the mindset. We make assumptions. One of the most deadly assumptions is that other people think the way we do, right? So here's a very difficult mathematical problem to solve. I'll give you a hint. The answer is 4. Okay. What we're assuming, though, is that we're in base 10 or anything base 5 or better, where there is a 4, right? And why? Because we've got 10 fingers and 10 toes, right? So you got to watch the assumptions. What is truth? I like some of these quotes, right? My favorite is Joe Friday from Dragnet, a 1950s detective TV show in America. Just the facts, ma'am. Just the facts? What's a fact? Interesting quotes over time. I like Homer Simpson. It's a joke until you get to recent times. In 2017, our press secretary gave alternative facts to that. The only alternative to fact is fiction. If you don't believe me, go down to the library, pass down the library, you'll see it. There's fact and there's fiction. There's no alternative fact. So this brings us to disinformation. Why would somebody discredit a scientist or somebody that's observing something, right? And this has been happening for a long time. Well, Galileo, was raked across the coals by the church because no, we can't have the earth revolving around the sun, right? It has to be the other way around. And how about the Scopes trial? I didn't evolve from no monkey. Well, okay. But that's so 20th century. But even in the 21st century, people hacked into servers to try to take a whole bunch of emails out of context in order to be able to prove that, climate change is a hoax. Well, no, it turns out not the case. So how do we compete with that? When there's paid disinformation to the public, how can the scientific community do its job to help society? How do you fight a war on science? You can't do it. It doesn't make sense, right? And people actually believe some of these things. What? So some people actually believe that there's some other way to draw a conclusion, to actually make a decision than observation, analysis, interpretation, and conclusion, which is the essence of science. Some people don't believe in science. Now, this goes back to wisdom given to us in 1972 by a blind black musician who knew something that we don't even appreciate now. When you believe in things that you don't understand, then you suffer. Superstition ain't the way, right? We still haven't quite figured that out. So we've got to work on that. And how do we do that? Well, there's some climate contrarians that would have you believe, oh, it's not happening, let's not worry about it, don't do anything about it, because we can make a little bit of money in the meantime. Well, is climate changing? I think most people will agree now it is. But then the next question, do people have anything to do with it? Well, that's where you get the science, or you get the IPCC, yes, but until you understand that people are having anything to do with it, no sense going on to discuss, is it bad? And bad is not a science term. Good and bad are value judgments, right? However, people, societies are very conservative. We like things the way they've always been. So that's a tough one. So yeah, it's bad. Can we do anything about it? The good news, it's not too late. And is it worth doing anything about? Thus we come to the cost of mitigation versus adaptation. So it certainly is. I've had some adventures and misadventures at the science policy interface at the local, national, and global levels. At the local level, the state insisted that the city of Philadelphia use more Pennsylvania fracked natural gas. Why? Not clear. Might be some politics involved there. So they built this cogen plant in Nicetown, which is an oxymoron. It's the worst neighborhood in Philadelphia. And they did this to burn fossil fuels coming from Pennsylvania, even when the Pennsylvania Electric Company had 80% of its power coming from non-fossil sources, right? And I had to explain as a expert witness that no, methane is not a renewable fuel. It's a fossil fuel like anything else. It turns to CO2 when you burn it, but you'd better burn it because if it leaks, which it does, it's 100 times stronger greenhouse gas than the CO2. So, but they built it anyway because of political pressure. So I took a couple of graduate students to Congress to speak to the science advisor of one of the Pennsylvania congressmen about the importance of climate change mitigation legislation. Discuss, okay, we need to do this. The advisor responded, well, why not just put scrubbers on the tailpipes of cars? I had to explain, well, we kind of do. We call them catalytic converters, and they remove the nitrogen and sulfur oxides that lead to acid rain, but the carbon dioxide still gets out. And that's the climate change problem. Oh, well, she responded, if we stop emitting CO2, all the plants will die, and we need them for food crops. Now, my graduate students were very polite and did not roll on the floor laughing, right? And I think, no, the plants are fine without our anthropogenic CO2. The scary part was that this was the person that our congressman from Pennsylvania chose as their science advisor. Disconnect between science and politics. Okay, so I was asked to go to the UN to reconcile the millennial goals of 2000 and the post-2015 agenda. And those together eventually became the Sustainable Development Goals. And one of the millennial goals was to eradicate poverty. Who can argue against that? Another one in the agenda, 2050, was halt and reverse climate change. Yeah, all for it. But these two conflict. Totally, right? Poor people don't change climate, only rich Americans change climate. And the planet can't even afford 300 million, never mind 8 billion more who want to consume like Americans. I had to go and misquote an old assassinated president, John F. Kennedy. Ask not what the impacts of climate change will do to the vulnerable and impoverished populations of the world. Rather ask what economic development of 8 billion people will do to climate change, right? Of course, this is the smartest people in the world at the UN. You'd think they'd have thought of this. And it highlighted then the importance of transitioning to sustainable fossil fuels and beginning to discuss in the UN, which they do not discuss, human population. Right? So what can we do? What can we do? In the end, basically, to maintain a future that we might wish, we have to avoid what we can't handle, right? Avoid the unmanageable so that we can manage what we can't change, right? So basically, mitigate what we can mitigate so that we can adapt to what we can't mitigate, right? So, all right, before I close, I want to thank a few very special people, right? Starting with the Armenian Society of Fellows, ASOF, that sort of got me involved in all this and introduced me to Alen Gasparian Abicharian, and Alen I met through ASOF. And then through Alen, I met Hajadur Meliksetyan, who invited me here 2 years ago to a conference which opened my eyes to look at all these great volcanoes in Armenia. And of course, to the National Science Foundation that have been supporting my research for now what has become many decades. Yeah, I'm old if you couldn't tell. And of course, to the Fulbright program that enabled me to be here this whole semester, to Lehigh University that allowed me to take sabbatical a year early in order for me to be able to do the Fulbright, and to Arevik, who hopefully has been not struggling, trying to translate all of this. So let me end with bringing us home. It's the only home we've got, right? How we manage it is going to determine the future of the geosphere, the biosphere, and human civilization. I'll end there. And are there any questions, comments, or outrage? Do you want to run around with a microphone? Oh, there's some over there.
Oh, our students, yes. Where are you guys? Two of them. Oh, our professors, maybe.
Yeah.
There we go.
I may have sufficiently confused everybody at this point.
Okay, I'll ask a question. When you were talking about the impacts of climate change, one of the questions was, is it a bad thing? And you said bad isn't a scientific term.
Right.
It's a value proposition. And throughout your lecture, it was very evident that change is the only constant, and it's still changing.
Absolutely.
So from a scientific perspective, how would you explain this? Or how would you answer it?
Change continues. Evolution continues. Now, human evolution is a little bit different because now we have medicine, right? We have medicine, we have welfare, we're concerned beyond, which we like to think of as civilization, which gets into sociology and philosophy, which are areas that I'm not fully qualified. However, change is going to continue. The extent to which we can steer that change, however, is growing. So we can steer the change more and more. What we've been doing is causing change haphazardly, randomly, right? So not on purpose. It's not on purpose that we started burning fossil fuels and changing the atmospheric composition, right? But we know it's been happening, so we can alter that if we want, right? So it's a question of what we do. The good news is that we can predict the consequences of our actions, which is something that previous species could not do, right? So we can predict it. So we know what's happening, a bit like Cassandra, right? So we can see what's going to happen in the future. What we do about it, though, that's up to us. And good and bad, I don't know. You know, maybe it's good for humanity to become extinct and for some other organism to rise up and develop intellect in a different way, right? So I can't talk about good and bad, right? But an interesting question to ponder over a beer or a wine.
Terence is our resident geologist, mineralogist, mining expert.
Thank you for that, Alan. I think the issue, as you suggested, was scientists inform politicians right. So the fact is that they get elected every 4 years, and scientists live for 50, 60, 70 years. Mm-hmm. So there's a quite a digression on that, right? So
Yeah.
how are you going to mitigate that? I'm not so sure, but we're trying. I guess you have some ideas as well to have a long-term view and consistent to be able to address the changes in politics.
Yes. For decades, scientists stayed away from the discussion. No political discourse. They would never even talk to a politician, wouldn't even try. Because if they did, it would be like they got their hands dirty. and they would no longer be respected by the scientific community. This has been changing, I hope, because I've been doing it a lot. So now scientists are allowed to speak to not only the public, but to policymakers, and that's important. I've spoken to a series of congressmen, in time as they go through, and representatives of a number of federal governments, to a number of representatives at the UN. And these cycle through much faster, like you say, than scientists. But there are career political figures that aren't elected, but they stay in Congress. They're the staffers. And those are the ones that provide some continuity in the US. I presume it works the same way here, because parliamentary, figures, they get elected every once in a while, but there are people that support them. They're the science advisors and otherwise that can remain throughout. So the temporal mismatch between the scientific career and a political career isn't quite as bad as it looks.
May I ask another question? You had one slide on plate tectonics.
Yeah.
The fact that we don't know much about the plate tectonics, the way that's going to progress or change. We have much better idea the last 60, 70 years than any time before in history. So how did that play a role in your, I'm going to say, factual presentation about these species? And the fact that the most recent serious plate tectonics was about 80 million years ago, 140 million years ago. And Antarctica still have 3 billion years of the plate tectonics at the basement. So we're moving around globally, which impacts the climate,
Yes.
which impacts the streams, the ocean streams, impacts the biodiversity. Okay, so this is getting very multivariate analysis. It's quite
Yes.
complicated.
Yes.
Instead of making serious one linear decisions. Correct me.
Yeah.
Thanks.
Tectonics does much more than merely keep some land above sea level, okay, because mountain building, right? It does more than that. It separates and joins continents over time and over the geologic time, even since the Devonian time of land plants. The last few 100 million years, the continents come together, separate, and when they separate, the species, the land species, not in the ocean is different, the land species are separated and then can diversify. So separated continents lead to greater biodiversity. When they come together, then all of a sudden, there's competition that wouldn't otherwise happen, right? So the competitive exclusion principle, they call it in ecology, where you can't get two species that do the same thing, living in the same niche at the same time, right? And we see this right now in England, where those big, bad, burly gray squirrels are killing off all the cute little red squirrels, right? So for a change from the North America to Eurasia, there's been an invasion. So continents do that too. In terms of where we're going, the rate of anthropogenically induced extinction is far greater than the rate of change caused by tectonics at this point. So let's deal with that. And then should we survive long enough to worry about what's going to happen from plate tectonics when the Atlantic Ocean opens, the Pacific closes, California encounters Japan, right? It's going to take some time. By that time, if we're still around, we'll deal with it.
But can I just add the question of whether the biodiversity we have now, that should be preserved. That's also a question to discuss, right?
Well, should it be preserved? Should is, again, not a scientific question, but we can say that if it is not preserved, there will be some consequences, right? So that we can say, that if we lose some species, some of which we don't even know yet, we may lose the opportunity to get some medicinals, for example. We may lose a diversity that enables new disease vectors to come and affect us, right? So, you know, all we can say is if this, then that. And then if we don't like the then that, then we talk about should with sociologists.
Thank you. Monica?
Hi, thank you for your talk. It's very nice. It's kind of a little catastrophic, right? You think, well, how we are going to go from here. But my question is more on the social, political, about society. And my impression is that you are talking to a very elite community, right? It's a very educated, you are talking to the heads of states, of multilateral organizations, and so on. And but what we have seen too at the same time, it seems to me at least, there is a proliferation and an expansion of fundamentalist ideas, terraplanist ideas, and all of these that are actually not scientific at all, and actually defy all of what you said. So what movements are being done, not just top down and top here, I'm talking about the intellectual, educated community, that sometimes, even though this part of this community also is believes in other things, or not even talk about the politicians who kind of deny it. But what has been done in terms of alliances and groups and conscientization of bottom up? How do we go not just for us, that is a small group, considering the whole 7 billion people, but on bottom up to make this more credible and a movement that is actually mobilizes masses and is more effective to some extent. I don't.
That is an excellent and very difficult question. You know, we want to avoid the situation of the Maoist cultural revolution, right? And how do we do that? You know, we have a war on science going on, and all this, right? And here we are, the scientific and intellectual elite, right? Here I am preaching to the choir, right? Rather than going out into the streets and the clubs and the people playing, you know, tavlu, or what do we call it here? Nardi, right? Right? Yeah, and in the park, right? And talk to these guys, right? So how do we do that? And we have to do that. And I'm because the message is not getting across. It used to be there's two branches in the American Geophysical Union of public outreach, and one is for speaking to policymakers, and you know, congressmen and senators and governors and that sort of thing, to get them to enact policies that are scientifically rational. The other branch, and I was doing that for a while, getting nowhere. The other branch is to learn how to speak to public in more public events. And I went and joined a club. This is a club of people that, you know, it's a social drinking club. I'm sure I was the only one that ever went to college, never mind PhD, right? You know, talk to people, find out what they're interested in, speak their language, right? Which I found myself able to do, and it's difficult to not feel like Jane Goodall, right? But you have to, right? You have to, you know, speak in terms that make sense so you can understand what they're thinking of, right? And how to communicate with them. We can't simply say, oh, here we are coming from high above, and we're going to educate you. No, I mean, they just won't accept it. So this is one of the challenges, but we need to do it better, and we need to reduce the divide between the intellectual elite, if you will, and the working man, right? So I think that's a very good point, and I've been doing what little I can, but we need to do much, much more.
Maybe last question from Molly, and then there is wine and reception after this. Please, we will go there. Molly?
Thank you. Thank you for this presentation. It rings very similar to that of the economist Kate Raworth. I don't know if you're familiar with donut economics, but
No.
She has wonderful resources on talking very much about what you're speaking of, and that is a paradigm shift from the growth GDP model of economics to one of sustainability. And with building on Monica's question and your response, I think in terms of informing and mobilizing, are you engaged at all in connecting the dots across? It's a both and challenge. Speaking to people on the ground, speaking to people in finance and economics and policymakers.
I've been speaking to as many as I can reach. I don't reach as many high financiers as I do policymakers and general public. Maybe I should. And it's it's a, so far as the policymakers are concerned, they'll do what it takes to get reelected, right? Or what their boss says to do for them to get reelected. As far as the general public is concerned, they'll do whatever they hear is the thing to do in the tribe with which they'd like to become associated, right? And a lot of that is done by personal word of mouth and conversations, like in this club and many other places. A lot of that now though, is changing to what they see in social media content, which is tailored to not only give them opinions, but to then reinforce them, which is leading to a greater divide politically, socially, and every other way. And here's AI can be our tool and our help. At the same time, it can be used to divide people. And the fascist maxim is divide and conquer, right? And in many ways, we're being divided and conquered, and we have to find a way to prevent that.
Thank you.
Okay. Հայրենով հարց չենք ուզում տալ, ընդհանրապես. Խնդրեմ, մի հատ հայրենով, one question in Armenian or more.
Շնորհակալություն, իմ հարցը հետևյալն է, գիտնականների մի խումբ հիմա ակտիվորեն ցանկանում է վերադարձնել կյանք արդեն իսկ բնաջնջված կենդանիներին։ Իմ հարցը հետևյալն է, դուք ինչ վերաբերմունք ունեք այս գործունեության նկատմամբ եւ ինչ բացասական կամ դրական հետևանքների այն կարող է հանգեցնել։
So the idea of the
հայրեն չեմ հասկանում։
So the idea of de-extinction. So this whole trend towards bringing back species that have gone extinct. What is your opinions? What are your opinions about de-extinction?
De-extinction
claims.
Yes.
Whether that's true or not, that's a separate question.
I think being good or bad may be dependent upon why they became extinct. If they became extinct because of our own actions and they would not have otherwise been extinct, then let's bring them back. If they became extinct for other reasons, though, no, that's not a good thing. I mean, think Jurassic Park, right? We could bring back dinosaurs, but mammals don't get along well with dinosaurs, right? So let's not mess with the natural order, as it were, of evolutionary processes, right? Sure, we should not cause more extinction or premature extinction, and if we can bring back those like the dodo bird, right, and many others that we have driven extinct, by all means, bring them back and then preserve them, as long as they naturally would be preservable, right? So we should, leave alone, like the Starship Enterprise's prime directive, don't mess with the natural order.
Okay, everyone. Շատ շնորհակալություն բոլորին։ Հիմա ֆուրշետ ունենք փոքրիկ միջոցառում, այսինքն գինի կա եւ այլն, so there's wine and there's a little bit of cocktail, small food for everyone to enjoy. Please join us.
All right. Kef time.